Just want to give you an overview of sort of what it is we do in the web handling world and what kind of things that you could imagine we're modeling. Let's talk about some use cases that have come from our customers. In this case, we're talking about accumulators. And you can chop a line and just take a look at a certain part of it. And that's what they were doing. They were looking at the buffering portion of the system and trying to find out if they could reproduce what they saw in their test machine. Now they're using it to optimize their buffers, the number of rollers, the location, the materials that go into those rollers in the buffer for their new designs. This is an interesting one because the problem a customer had been having with a given machine, really the issue boiled down to the materials that were coming into that wine drum had different thicknesses. And these would cause abrupt changes to the radius of the wine, which meant that there would be tension changes and speed changes that would then propagate into the system. Simulation helped discover this, and then simulation provided a playground or a test bed to come up with solutions to remove those fluctuations or vibrations that they were getting as a result of these abrupt changes to the radius. And I should say, we actually didn't have a component in MapleSim to model this kind of phenomena until we had this discussion with the customer and working with them, and we subsequently built that in. And so now when you grab MapleSim, a component that allows these kinds of capabilities is available in the product. And that's how actually a lot of the new pieces coming into the tool, it comes from our work with customers and new phenomena we encounter as we're working with them. And this last one is slightly different. This is where a customer wanted to get into a new field they weren't familiar with, Z-fold battery construction. And so they used our tool to say, hey, let's try out some different designs. We can use it for motor sizing. And before we build something, we can have a good idea of a lot of pieces of the puzzle before we actually start building this thing. Let's have a discussion about what the problem solving looks like for an engineering team. So they're there and they get told, hey, we've got a new design. Now it might be a new design that they have no familiarity with, or it's a new type of product that they want to get into. And so you want them to sort of start coming up with ideas for how are you going to build this new machine and this new sort of roll-to-roll process. Sometimes, and I mentioned it previously, new materials come into play. So you've got a machine already, but it was designed for a different purpose, a different material. Maybe government regulations have come in and said it has to be thinner, or it's got to be some material that is more easily recycled. And so you've got to change your system of a current machine to fit a new set of criteria that you're working towards. Often, you've got a machine that's out there that's now starting to show some quality issues. Maybe you've got some tearing happening or some wrinklings going on, and you want to track down what's going on there and get that problem solved. And if you have no quality issues, it's a design you know about, everything's running well, there is someone who's going to say, I want it to run faster. And at that point, you will probably start running into quality issues as you turn the speed of that machine up. So how do these problems get solved? These things come up, the engineering team gets faced with them. What do? Well, the engineering team is clever. They come up with solutions, right? They come up with an idea of how they could solve this problem. And they say, okay, here's where I think we should, maybe if we increase the wrap angles, we're going to move these rollers. Great, we'll try that out. So they pass that along, you get technicians coming along, they start doing work and move along. Maybe you build a prototype machine and you start moving things around on that machine and you test it out. Now, if you're lucky, the technicians will record data coming out of the machine. You can analyze that data and say, hey, does it solve our problem? And if you're lucky, maybe you only have 1 or 2 passes through this. But often you get this back and you just keep doing this process. And we've come alongside customers who've had a sticking issue for months. And they've come along and said, we're just having a hard time getting to the bottom of this. And part of the issue is just the time it takes and the cost involved for each of those loops. So let's look a little bit at those challenges, right? So first thing, engineers don't necessarily have a full picture of what's going on. The second one is that every time you do one of these tests, it costs money. Now, some areas running the material's not that expensive, it's not a big deal. But in some areas, particularly battery, you have pretty expensive materials, and you guys can calculate on your side what it costs to run each one of these tests and sort of throw away that material each time. And even if your material isn't expensive, there's people's time. You've got your engineers looking at this problem. They could be looking at other things, but they're focused on this. You've got technicians involved who are updating the machine, who are pulling the analysis results to give to the engineer. Like, you've got a whole process going there that costs time and money. And then the last piece there, of course, if you don't have a prototype machine and you're working on something that's actually in production, there's costs associated with downtime. So if you want to ask the question, why bother with simulation? I mean, the ideal goal of simulation is that it can kind of replace itself in that loop. You can come up with that idea, you go to implement it, well, you're implementing it in the software where it's quick to do, and then you can do that iteration faster, right? And because it's software, we don't have to worry about load cells because we have all the information. You can see the tension in every span. You can see what the wrap angle is as that dancer moves. You have all the information for your engineers to make decisions. Obviously, you're not generating any material waste because it's a virtual machine, and the timing to do this is much quicker. It's very fast to take a roller and move it and try out the simulation again and see how that changes your results. And then finally, obviously, you don't have issues with production because that isn't the machine in production, it's the virtual machine. A fair view of a loop is what you see here. So you're presented with the problem, the virtual tests are happening, so you're looping on that and you're solving it and getting an idea, but you're doing those in fast iterations, right? You can test things out quickly. Once there's something that you feel satisfied with, then you can take that and put it in and do a physical test, which is the sort of more expensive and costly loop. Why bother with simulation? When you're trying to solve a problem, it allows you to quickly iterate on your problem without having to go through that slower and more expensive testing on the physical system. And really the big goal here is to give your engineers insight into the problem, because if they have insight and can see the big picture, not only can they build better machines, but they can get those products and solve problems faster. That we help our customers design better machines and solve complicated problems with tools and services. I hope you have a better idea of what that looks like in the context of MapleSim simulation.